Hey everyone, Geophysicist Stefan Burns here. We have just observed a major disruption to the polar vortex, sending a bunch of snow and wind and ice, sleet, slush, and more out of the Arctic Circle further south, down into North America, even down into the southern states, into Europe, into the UK, into the far east of Asia, down to Japan. So there's been a tremendous amount of snow. There's been record snowfall in a variety of locations around the globe just over the past week or so. And this is because of the disruption to the polar vortex. We have more volatile climate here on the planet that becomes more and more disrupted, but this isn't a one-time thing. In fact, we just had a really big space weather impact with a G4 geomagnetic storm and also an S4 radiation storm, the strongest in 20 years, which is very likely to keep the disruptions to the polar vortex continuing on for the remainder of winter and into spring. So this is not a one-off event. In fact, I think that we're going to be seeing a lot more volatile weather in the northern hemisphere as a result of this, because these solar protons and ions and alpha particles and more, and I'll explain all this as we go, funnel down into the Arctic Circle because that is where the magnetic field cusp is located. So pretty strange that we had this strongest radiation storm in 20 years, and then right during that time frame and immediately afterwards, we saw this massive disruption to the polar vortex. Here we're looking at snow depth for today. Right now, we see that there's tremendous amount of snow across the northern hemisphere, specifically in the high latitude regions. Of course, that makes sense, but we also see it having extended further south than maybe normal. It's not like we had massive blizzards, but this is definitely a pretty big disruption that has come about. We can see our 2-meter temperature anomaly here. We see that we have some really cold temperatures here in Eurasia, for example, Northern Europe, and then also really down into the south there for North America. And you see that we have these high temperature anomalies in areas that are typically cold. That is the disruption to the polar vortex. If you look at our average temperature right here, we see that just in general, there are some frigid temperatures that are active right now on the planet. What is our polar vortex? We can look at that right here. So this is a stable polar vortex. It's a circulation in the atmosphere that goes from the troposphere where we live, the lowest part of the atmosphere that's the most dense, all the way up to the stratosphere. And this is key as it relates to connecting it to space weather and solar storm impacts, because they charge up the ionosphere, and the stratosphere and the ionosphere, they overlap with each other. And if you have a really strong radiation storm, those particles, highly energetic, can pierce further down into the atmosphere, for example, into the stratosphere. So when there's a stable polar vortex, the cold air is contained, and you have this jet stream flowing like this. But when you get a disrupted polar vortex, you see that all of a sudden this jet stream starts to undulate. It's more like a river, kind of flowing, a meandering river. It can pinch off and all this stuff. And we have cold air move south. And then you typically will see warmer temperatures in the area where there originally was that stable polar vortex. So that's what we're seeing right now. This warm air move north. We're seeing this cold air move south. And that's really hitting North America and Europe and Far East Asia there, with Kamchatka seeing record snowfall in 60 years. That's the peninsula for Russia. And then also Japan seeing some really high snowfall. We're seeing a blizzard come into the United Kingdom right now. Wavy jet stream dumps record snowfall on Russia. This was posted back on January 20th, right as this solar storm impact was coming in. So the key thing to keep in mind here is that space weather does not create these weather systems in general. It just will intensify anything that already exists. It'll make it more volatile too overall. So we already had this disruption starting to occur, and then you have this impact. It's only going to make it bigger, more intense. And for a S4 radiation storm, an impact of that level, we're looking at changes not only weeks from now, but also months and even years from now to our radiation environment, our plasmasphere environment surrounding the Earth. So these sort of disruptions are not a one-off. We're likely going to see a more unstable polar vortex going forward for the remainder of winter all the way to spring and perhaps even into like next year. So this could last some time. Russia's Far East is buried by its heaviest snowfall in 60 years as a winter blast swept across Asia. We can look here. Heavy snow and ice impact millions as winter storm sweeps across the United States. 84,000 power outages. I think it's like 1 million plus people without power. There have been some casualties, unfortunately. This has been a very significant snowstorm, especially here in the South where they're not used to this. Tremendous amount of ice and sleet and more. We've had some snow where I've been about a foot, but it hasn't been too crazy. Here we see record snowfall leaves cars struck and people stranded in Russia's Far East. Again, it's been tremendous in Russia. And heavy snow hits wide areas of Japan as extreme cold front hits. This is on the 21st of January. And this was more northern Japan, like the Sapporo district area, that prefecture. But overall, there's been just a tremendous amount of snow. And we can also look here, snow map reveals snow bringing 69 inches to parts of the United Kingdom, 90% of the UK, including London. So this is a big blizzard that's about to roll through. You see that this was published just today. So this is the ongoing disruption to the polar vortex, bringing a ton of cold weather further south than normal, which is normally contained up in the Arctic Circle and those lower latitude zones just around it. And here we have a visualization tool which allows us to see this polar vortex in action across a variety of heights. We use pressure to show those different heights. So this is all measured in hectopascals. So we see this right here, this jet stream at the highest most part of the atmosphere, really plunging down south into the United States and also across northern Europe there into Siberia before then jutting back over. We see a smaller circulation there over the North Pacific and parts of Asia. That is at 10 hectopascals. That is very high up. We can typically look at the stratosphere with about 50 hectopascals, and that's typically where the polar vortex will extend up to, especially during the winter. So we are now looking at the polar vortex very specifically at the higher stratospheric levels. We see again it plunging really down south into North America, and we see that it has this bifurcation there. That is where it's split apart. We have this warm air moving north. We see that also plunge down into Europe like this. If you go to 250, then we see a greater disruption. This is closer to the troposphere, the type of, the part of the atmosphere that we live in. And we see that it's really extending far south here. Again, look at how the south of the United States has really been hit by this disruption. And if you go to 500, then we see that as well, still also really hitting the south of the United States. And then there's a lot of volatility at this level, which corresponds to about 5.5 kilometers or about 17,000 feet or so. So this is the state of the polar vortex at this moment in time, and all those charged particles from space are coming in this location, further disrupting the volatile system that already exists here. Again, we see that bifurcation of the polar vortex very clearly there, and the magnetic pole is right there. It's right in this location, so it's funneling right to where it's splitting apart, showing it's directly connected to that polar vortex in location, and we know there's a huge amount of energy coming in from our space environment. Here's a visualization showing you these polar cusps because it's really made clear when you see where they're located. So we have Earth, it has a magnetic field, we see solar wind, or imagine this is a solar storm. These are all particles that were launched from the sun coming in. You see that they funnel down here, and in the northern hemisphere, they funnel down to where the magnetic pole is, which is right now located very close to the actual rotational North Pole, and that's the magnetic cusp. It's a bit of a wider zone, and it funnels down to this system. So you see these particles, because they have charge, they are guided down those magnetic field lines. The force of the magnetic field is so much stronger than the force of gravity. They have a little bit of mass, but electromagnetically, they're guided down, and then they go to the atmosphere. We get aurora, and we also get a whole bunch of other phenomena to occur, but that is in fact, in general, putting a tremendous amount of energy into these regions. So during normal space weather conditions with ambient solar wind, you do have this particle flux, but during a very powerful solar storm, which we just had, then this can get greatly amplified. We can see specifically our space weather timeline here. This is going back to about the 18th of January. We see that we had a 1.9 X-class flare. That's the strongest designation. The three strongest go from C to M to X, and that is a 10X jump in energy each time. So 1.9 long duration X-class flare is a big deal. We see immediately our proton flux. This is hydrogen ions. So just a single proton zooming through space. It's been stripped of its electron. It may have a neutron attached. In general, it doesn't though. And we see that that went up all the way to S4 levels. It caps out at S5, and we've never seen an extreme S5 radiation storm. So this right here is either the fourth or the fifth strongest radiation storm that we've ever observed since records began back in the 70s. Very significant. We're talking like 5 orders of magnitude increase here in particle flux. So that's 10 times 10 times 10 times 10, right? It's massive. We see our interplanetary magnetic field as a result of that solar storm shock. It was record values effectively, going up to 90 plus nanotesla. Normal field strength for the solar wind is 5, and typically for like a strong or even a severe geomagnetic storm, you're looking at field values of 30 to 40, maybe you're touching 50. It's very rare to go above 50. That is very significant. We had values of 90. The only reason this solar storm wasn't the strongest since 1989 or even before that was the fact that the magnetic field had a positive polarity, to keep it really simple, and you need a negative polarity to connect to Earth's magnetic field. When it's positive, they kind of bounce off each other. If this had been a negative polarity solar storm, it would have been the strongest by far since 1989, and I think actually probably even stronger than that, and that was a big solar storm. But the last S4 radiation storm was the 2003 Halloween storm, so that's like 23 years ago now. So it has some very unique characteristics. You see here how our proton fluxes remain elevated all the way up to today. It has been diminishing now, but it is still elevated over normal. That will probably come back to baseline within the next few days. We see that our solar wind here went all the way up to about 1,200 kilometers per second. It really peaked at around 1,100 kilometers per second, stayed at 1,000 for a while, and then eventually dropped down. We're back to more normal solar wind speeds. That was a very fast solar storm impact. We have seen faster before, but not that many. This was one of the fastest in a long time. And we see that our KP index, a measure of geomagnetic volatility, basically went straight to the top and maintained very high levels for more than 24 hours, about 36 hours there, where we were at very strong geomagnetic storming. It was a G4 severe storm, and we even reached G5 minus levels. So that's an 8.67 on the KP index. So this was a big solar storm, an even bigger radiation storm, and all that energetic flux is going into that location where the polar vortex is. So I showed you this visualization here of Earth's magnetic field and the solar particles coming in, then flowing down the magnetic cusp, and we also see our polar vortex. You see the location of that is where we have that magnetic field cusp. And so we can also see here ion precipitation. When these high energy particles come in, they will then hit other molecules and ions in our atmosphere and charge them up. And they're coming in at speeds that are close to the speed of light. That's relativistic speed. So this is relativistic ion flux, and it's just tremendously powerful. It doesn't just trigger one ion to energize. It actually creates a cascade of them. So thousands and thousands of particles, molecules, ions will suddenly increase in their energy, and that has a dramatic effect on the overall electron density profiles or the conductivity of the atmosphere. And that is key as it relates to storms and snow and all this stuff, ice formation. That is all driven by electrical dynamics in the atmosphere. And so especially with like ice particles in the atmosphere, they also accumulate charge. When they rub past each other, they build up a charge. Well, you're going to have greater charge building when you have a stronger electric current going from the ground surface up to the ionosphere, and also the polar vortex disrupting that whole flow going from the troposphere to the stratosphere. All that's going to get amplified. So we see big changes across time due to all of this. Here we see the afterglow of that geomagnetic storm, and the sky continues to glow green for days after severe geomagnetic storms are over. Here we see that from France, and you see that there's different colors at different levels. So this isn't aurora, this is just overall energetic flux manifesting, creating a little bit of visible light that we can see, especially under dark sky conditions. We had the new moon on the 18th, which made it perfect conditions to see this sort of afterglow. It's a chemiluminescent process in the upper atmosphere, normally energized by sunlight, but geomagnetic storms can do the same thing. When Earth's magnetic field opens up, allowing solar wind energy to be stored in the magnetosphere, it is then released into the upper atmosphere over subsequent nights. And that is because we have these radiation belts that surround our planet. That is what undergoes these long-term changes after really, really big solar storms. Profound changes of the near-Earth radiation environment caused by solar superstorms. And I'll link this in the video description if you want to read it. You can also throw it into like Notebook LM, get a podcast, learn a little bit more about this in a fairly easy to do manner. But we can look at our abstract here. The outer radiation belt is often enhanced during storms, while the inner belt is usually considered to be unaffected by geomagnetic activity. During the most recent Halloween superstorms, you'll keep in mind that that's when the last time we had an S4 radiation storm, right? We saw an extreme erosion of the plastosphere, which allowed particles to be transported closer to the Earth, where they were then locally accelerated. During such a strong event, electrons will be transported into the heart of the inner zone, where they will then be accelerated by chorus waves. And when the plasma pause extends to larger distances, electrons accelerated by resonant wave particle interactions in the inner radiation belt will find themselves in a very different plasma environment, and strong fluxes may persist for several years after such a storm. So what just occurred is not just we had 36 hours of intense geomagnetic volatility, and then we had a few days of afterglow, and the radiation storm is just now petering out. That's it. That's all she did. Like, we're talking about long-term changes here, and because of just how powerful that solar storm impact was. This was a solar superstorm for sure. Again, the only reason we really got lucky was because of that positive magnetic field characterization that it had, rather than it being negative. If it had been negative, we probably would have been looking at some power grid outages, telecommunication issues, satellite disruptions, GPS would have gone down, and basically not been usable, radio blackouts, and basically tons of problems. So we're very lucky that we had that positive field, though it diminished the aurora that we saw overhead, but that's a small price to pay. So these changes can persist for several years after such a storm, and we are just a few days after that now, just about a week after that storm occurred. And well, we have a lot of winter and spring left in the northern hemisphere, where we can get these sort of big snowstorms and more. So this was a very powerful radiation storm which caused long-term changes to the radiation belts, which we see right here with this model. Here's the magnetic field. Here's those polar cusps where the particles flow down into them. And one thing to keep in mind, you may be wondering, why am I not talking about the southern hemisphere? You have these particle dynamics that exist there as well. But in general, we seem to see greater impacts of space weather during winter than we do during summer for our weather in the atmosphere. So right now it's winter in the northern hemisphere, which is why we're focusing there more at this moment in time. But if I click forward, you'll see that these all of a sudden really drop down in their flux. There is our scale bar there. Huge impact, right? A massive precipitation event into those parts of the atmosphere, the ionosphere, even deeper down where that polar vortex extends up into the stratosphere. And we now have been recharging. Here we see some of that volatility across time. And again, we're looking now at a different radiation belt environment going forward for not only the next few days and weeks, but months and perhaps even years. These changes take a long time to unfold. They are also subtle, and they become less and less significant over time. But I would say definitely for the remainder of this winter and spring, when we have the chance of there being snow in the northern hemisphere, especially if there's more disruptions to the polar vortex, this dynamic is certainly at play, and it's going to make everything more intense and more volatile. At least that is what the best research indicates. And so you may be asking yourself, well, did we see any evidence of this? And well, this is one data point, but this is quite bizarre. It's not like we've never seen this before, but we saw lightning during this snowstorm and ice storm in South Texas. So here we have a video of that, and you'll see the lightning flash, you'll hear the thunder. This is quite bizarre. You typically don't get lightning during, snowstorms, or else that'd be a common thing. You typically need hotter, more moist systems going through, like during the summer, to get thunder and lightning. And so that shows that there's a tremendous amount of electrical energy in the atmosphere in these storm systems, even though they are chilled down below the point of freezing. So this is just some really good evidence out of South Texas, mind you, that there is a tremendous amount of excess energy right now in the atmosphere as compared to normal because of that solar storm impact, but really specifically from that S4 radiation storm. So while right now a lot of people are talking about the weather that we have coming up tomorrow, the next day, or maybe even looking, let's say like 7 to 10 days out, and these sort of weather models which can predict that are typically pretty tenuous. They are not that accurate, though you can kind of get a sense of what may be coming 7 to 10 days out, but that's where things start to break apart. There's no one out there talking about longer disruptions to the weather, and that's because they're in general not educated on space weather and the connection between space weather and terrestrial weather. And so it's good to have an outlook going beyond just, let's say, 5 to 7 days, but actually going out months and months, all the way to the end of this wintry season. So that is the point of this video. I also wanted to educate you on the connection between space weather and our weather environment here in the polar vortex, and how all of these energetic systems are connected together. So if you'd like to learn more about this, then please subscribe to the channel. I cover everything that's happening here on Earth energetically with videos almost daily. So we're talking earthquakes, volcanic activity, severe weather, geomagnetic storming, but we also look at, for example, space weather, solar activity, planetary alignments and resonances, interstellar and cosmic forces. Everything and more is covered. I've been your host, Stefan Burns. Thank you all so much for watching. Hope to see you around. Smash that thumbs up button to help the channel grow. Please subscribe. And I'm wishing you all a great wintry season. I hope that none of you have been too severely impacted by all these wintry, snowy conditions. If you're on the southern hemisphere, I hope it's not too hot down there. I also know that's also some pretty hot, severe weather down there as well. So just in general, we're looking at more intense and volatile weather going forward. Right now at the end of solar maximum, the beginning of the descending phase, a tremendous amount of energy has been pumped into the Earth as a result of this. So do what is necessary to be aware of that, to be prepared. Do your own research. Links in the video description. Thank you all so much. Have a great day, and I'll see you all in the next video.